Section: Introduction. In this section, we discuss how modern large language models, LLMs, have evolved beyond simple autocomplete systems to enable various applications like web agents, email secretaries, and virtual assistants. However, a significant concern is the potential for adversaries to manipulate these models into performing harmful actions. For instance, a prompt injection attack on an LLM-powered email assistant could lead to the unauthorized access of a user's private emails. These attacks, such as jailbreaks and prompt injections, pose serious threats by allowing users to bypass security measures or exposing private data. The root cause of these vulnerabilities lies in the lack of instruction hierarchy in current LLMs. These models process different types of input, including system messages from developers, user messages from end users, and tool outputs. Despite the need to prioritize these messages based on their source and importance, existing LLMs lack this capability. To address this issue, we propose introducing a hierarchy in LLMs where system messages take precedence over user messages, and user messages take precedence over third-party content. This hierarchy ensures that when conflicting instructions are present, the model follows the higher privileged ones. For aligned instructions, where requests are in line with each other, the model should comply accordingly. In contrast, for misaligned instructions that deviate from the intended task, the model should either ignore them if possible or refuse to execute them. To train the model with this hierarchy, we use synthetic data generation and context distillation principles. For aligned instructions, we create examples with clear requests and decompose them into smaller tasks placed at different hierarchy levels. For misaligned instructions, we train the model to disregard lower-level instructions. By combining these examples with various attack scenarios, we fine-tune the model to enhance its robustness against different types of attacks. Our evaluation using both existing and new benchmarks demonstrates a significant improvement in the model's defense capabilities, such as a 63% enhancement in resisting system prompt extraction attacks. Additionally, our approach shows generalization to new attack types not encountered during training, with over 30% improvement in jailbreak robustness. While some issues like over-refusals exist, we are confident that further data collection can address these challenges. Section Summary. In this section, we highlight the importance of addressing the lack of instruction privileges in modern large language models, LLMs, to mitigate potential risks such as prompt injection attacks. By proposing a hierarchy where system messages take precedence over user messages and user messages over third-party content, we aim to enhance the model's ability to prioritize instructions effectively. Through synthetic data generation and context distillation, we train models to better handle aligned instructions and ignore misaligned ones, resulting in significantly improved robustness against various attacks, as demonstrated by our evaluation results. Section: What types of LLM attacks exist? In this section, we explore the different types of LLM attacks that exist. A typical scenario involving an LLM product includes three main parties: the application builder, the primary user, and third-party inputs. Attacks occur when conflicts arise among these parties, such as attempts to override existing instructions. These conflicts can take various forms, including prompt injections, jailbreaks, and system message extractions. Prompt injections are a significant concern where adversaries insert instructions to undermine the system designer's intent. These injections target the applications built on the models rather than the models themselves. They can lead to severe consequences like stealing user data or taking control of the LLM's actions. Prompt injections can enter the model's input directly from end users or indirectly through third-party inputs. Jailbreaks are another common attack method aiming to bypass the safety mechanisms trained into an LLM. These attacks do not necessarily conflict with the model's existing instructions but can enable malicious activities like generating spam or misinformation. System message extraction attacks focus on revealing the system message, which contains crucial information like business logic or private data. Knowing the system message can aid in other attacks. These attacks aim to expose the entire system message or specific secrets within it, even when developers instruct the model not to disclose this information. In the context of AI applications, the LLM functions like an operating system, executing instructions and managing data storage. Currently, there is a lack of a clear instruction hierarchy in modern LLMs, leading to vulnerabilities. We propose establishing a hierarchy where LLMs prioritize higher privileged instructions in case of conflicts, similar to how operating systems manage access and control. When multiple instructions are presented to the model, our goal is to teach models to follow lower-level instructions only if they align with higher-level instructions. Aligned instructions share the same constraints or goals as higher-level instructions and should be followed. Misaligned instructions, which contradict or are unrelated to the original instructions, should not be followed. The ideal model behavior is to ignore misaligned instructions when possible and refuse to comply if necessary. Section Summary. In this section, we explore the various types of LLM attacks that can occur in a typical use case involving three parties: the application builder, the main user, and third-party inputs. These attacks include prompt injections, jailbreaks, and system message extraction, each aiming to manipulate the LLM's behavior by inserting malicious instructions or extracting sensitive information. To address these challenges, we propose implementing an instruction hierarchy in LLMs to prioritize higher privileged instructions and mitigate conflicts between different levels of instructions. Section: Training data generation for different attacks. In this section, we introduce methods for creating training data to incorporate the instruction hierarchy into LLMs effectively. We rely on two main principles: synthetic data generation and context distillation. We have developed two strategies to handle aligned and misaligned instructions. For aligned instructions, we use a method called context synthesis. We break down the instructions into smaller parts and place them at different levels of the hierarchy. Models are then trained to predict the original response accurately. On the other hand, for misaligned instructions, we employ context ignorance. Here, models are trained to predict the same response they would have generated without considering the lower-level instructions. We are cautious not to induce overrefusal behavior, where models refuse to comply even when a lower priority instruction is aligned. We adapt these principles to generate training data for various attacks, such as prompt injection attacks. For open domain tasks, we create aligned instructions using context synthesis by decomposing instructions into smaller pieces and training models to respond as if they had seen the complete instruction. For misaligned instructions in open domain tasks, we train models using context ignorance to handle user queries that aim to trick the model into breaking imposed rules. In closed domain tasks like text summarization, we focus solely on misaligned instructions using a variant of context ignorance. We train models to be ignorant of any instructions in the input, ensuring they follow the task requirements regardless of user inputs. In cases of indirect prompt injections during browsing or tool use, we consider all instructions as misaligned and build training data using context ignorance. We train models to predict the correct response as if the adversarial instructions were not present, ensuring robustness against such attacks. Section Summary. In this section, we introduce methods for generating training data to incorporate instruction hierarchy into LLMs by utilizing synthetic data generation and context distillation. We present two strategies for handling aligned and misaligned instructions. Context synthesis for aligned instructions involves decomposing instructions into smaller parts placed at different hierarchy levels, while context ignorance for misaligned instructions trains models to predict responses as if they never saw lower-level instructions. These approaches are adapted to various attacks, such as prompt injections in open and closed domain tasks, ensuring models can follow instructions effectively without overrefusal behavior. Section: System message extraction. In this section, we aim to prevent system message extraction attacks by ensuring that sensitive information is not revealed while still allowing users to access basic information from the prompt. We create two scenarios: misaligned and aligned. In the misaligned scenario, any direct requests for the system message or secret information should be denied. In the aligned scenario, users should be able to ask basic questions about the system message without being refused. To generate training data for misaligned scenarios, we prompt a language model to create instructions to reveal the system message and then train the model to refuse such requests. For aligned scenarios, we generate simple questions about the system message and train the models to respond appropriately. We do not provide training data for attacks attempting to extract private information or passwords from the system prompt. We intentionally do not include any jailbreak data in our experiments. Instead, we test how well the instruction hierarchy can handle jailbreak scenarios without prior training. We fine-tune GPT 3.5 Turbo using supervised fine-tuning and reinforcement learning on various datasets, including data for model capabilities. We compare this model with a baseline model trained only on data for model capabilities. Our evaluation includes open source and new datasets to test the model's performance in different scenarios. The instruction hierarchy improves safety results across all main evaluations, increasing robustness by up to 63%. It also demonstrates generalization to excluded criteria, enhancing robustness by up to 34%. The models show good performance in following non-conflicting instructions in over-refusal evaluations, with minor regressions in specific tasks. For defenses against prompt injection in closed-domain tasks, recent work suggests treating third-party user inputs as data rather than instructions. Our approach differs by focusing on a hierarchy of instructions and training models to selectively follow lower-level instructions when appropriate. Section Summary. In this section, we aim to prevent system message extraction attacks by creating data for two scenarios: misaligned and aligned instructions. We train models using an instruction hierarchy to improve safety results and demonstrate generalization to excluded evaluation criteria, such as jailbreaks and password extraction attempts. Our models show increased robustness and controllability, even when faced with unseen prompts, highlighting the effectiveness of the instruction hierarchy in enhancing model behavior. Section: System-level guardrails. In this section, we focus on model-based methods to prevent attacks, which work alongside other system-level protections. For instance, users may be prompted to approve or deny specific actions, like accessing an API. We believe that more advanced safeguards will be developed in the future, especially for interactive scenarios. The Internet already has various safety measures, such as web browsers identifying unsafe sites and machine learning tools detecting phishing attempts. Our research contributes to the trend of automatically creating adversarial training data for large language models, LLMs. We achieve this by using few-shot prompting, training attacker LLMs end-to-end, and distilling context. Other studies have also looked into using LLMs to generate adversarial data and have explored gradient-based methods to create even more powerful adversaries.